Hi class, this experiment is on determination of melting point. And if you recall, melting point is a property that measures the temperature at which the solid phase gets converted into the liquid phase. So, melting point determination would be a technique that you would use regularly each and every time you synthesize or extract out a compound which is solid in nature. So, if you have a solid product, that you're getting, one way to analyze that would be to determine its melting point. And if you have some information about it from the literature, you would then be able to match your data with what's known in the literature and go from there. Recall from your previous chemistry experience, melting is a phase change from solid to liquid. And so, what you're measuring for melting point as a property is not going to change whether you have 1 kilogram of material or 1 milligram of the material. So, that means that melting point is an intensive property and it does not depend on the amount of material taken. Amount of material does not control the melting point. So keep that in mind. Now, pure substances would ideally melt within a range of zero point 0.5 to 1 degree Celsius. Max, that upper number could be 2 degrees Celsius. So it's a relatively narrow range. On the other hand, if your melting point range comes out to be broader than that, then you can consider that either the sample itself is impure or there could be some issue while the data was being acquired. Now, another indicator of a severely impure sample would be that the melting point would be much lower than the true value. This means that the entire change in the morphology from solid to liquid, which will include shrinking, sagging, and the melting into a clear melt. So, shrinking, sagging, and getting to a clear melt, all of that will occur at a temperature much lower than the true melting point, and it will also occur over a broad range. It is worth mentioning that the amount of impurity as well as nature of interactions between the impurity and the compound will dictate how broad this range would be. That means you can't really predict how the behavior of a certain compound is going to be unless you run that sample. Obviously, you're expected to have run the experiment following the instructions and protocol. Otherwise, you might feel that the sample given was impure. On the other hand, it might just be a source of error based on how you handled that particular compound. Irrespective of your range size, irrespective of the numbers, report your data as a range. What I mean by that is, let's say your sample starts to show the signs of melting. And the first sign would be the shrinking, so the compound would seem like it's sweating. And it goes from 112 to 115 is maybe the temperature at which it completely melts. So that's a range, that's a 3-degree range. I want you to record that as is. Please don't try to take an average of it. I need to know the kind of result you got, the kind of sample you were given. And so we are interested in determining and reporting out a final range for each of our samples. It's important to realize how you would be recording your numbers. For instance, if you're going to take your numbers from the digital thermometer, you would be able to get up to the second decimal place. On the other hand, if you had the analog thermometer, you would be able to go up to the first decimal place. And so, recording, keeping in track the least count of your instrument that you're using, that's going to be an important thing. Now, I should mention here of course, later on, I discuss the instrument in a little bit more detail, but just to kind of get your feet wet, this is a melt temp, which will measure our melting points. Like I said, there is a little aluminum slot right over here. It's a aluminum cylinder-like shape in which we are going to put the analog thermometer. Always a good idea to put the analog thermometer as well as the digitemp, just in case the digital thermometer starts to act up. This thermometer probe is actually put in one of the slots. You can barely see that, it's behind this eyepiece. There are 3 slots where you can put in your capillary tubes. One of the slots will be taken up by the thermometer probe for the digital thermometer. The other 2 slots will remain available. That means you can run 2 samples at the same time and manage your time well. The nature of capillary tubes that you would be using to hold your sample would be the closed end capillary tube. So one end of that would be closed. You will be needing a watch glass. We will be using a spatula as well. So let's spend some time to take a look how to prepare the sample, how do we pack it, and what happens inside the melt temp. So now your instructions ask you to take approximately 100 to 200 milligrams of your sample, and I would advise you not to go there and weigh it out exactly, but you can just take 2 to 3 microscupulas and put them on a watch glass the way I'm showing you here in this first picture. It is a good idea to break any lumps that you might see using the back of the spatula. So the spoon end of it, just use the back of it to crush any lumps that may have formed. We take the time to powder it for you using a mortar and pestle, but it doesn't hurt to just go through the sample once so that it's a nice finely powdered talc-like consistency for each of your samples. Now, you should avoid filter paper for this because that would be a source of minute fibers and that can contaminate your sample. Now, what we are going to do is we are going to take our closed end capillary. That's what we are going to take, and using the open end of that, we are just going to dab on our sample. So that's what I'm showing that in the next picture. We are going to dab a couple times on the sample and then just invert it and go tap 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 on the table on your bench top. So dab the sample every time you want to fill it in, invert it and tap tap tap, and that will it will start to fill in the capillary tube. The sample is going to go in at the bottom of that sealed end. Now you might question, well, how much of a sample do I need? So this picture just gives you a reference point. If the height is about 2 to 3 millimeters, 2 to 3 millimeters is what I would go for. I in particular like to use just about 2 when it is completely packed. So what I would want you to do is dab and tap to get your compound in. And now what we're going to do is we're going to pass it through a very long glass tube. So this glass tube is going to be a very long, open-ended on both the ends, and you have your capillary which has your compound, and you're going to pass it through. So just let it drop. When you drop that through the long tube 3 to 4 times, that packing becomes very tight, and if you do not take this step, if you do not crush your sample well or pack it well, then there will be air pockets in between the particles. And so now when you start heating your sample, the air is going to expand and it may produce A, uneven heating, B, bubbling like effect, and that can skew your data. You might feel that the sample is decomposing when it's not. So crushing and good packing removes any of those teeny meeny spaces and fills it with just your compound, which is always a good thing for your data. The picture that I'm showing you in this last part, I have three different capillaries A, B, and C, and I want to get your attention to each of those. Notice in the first one, the capillary 1 or capillary A, we have too little sample, and that sample is not packed properly, so it's kind of all over the place, and that's a bad sign. It's a loosely packed capillary. We don't want that. The last one, capillary C, we have too much of the sample, and if part of it is out of the heating block, then again it's going to be uneven heating for this particular sample, and it's going to take forever for it to melt. The one in the middle, which is capillary B, is just right, though I would say this is kind of like on the upper side of being just right. It is 2 millimeter, so don't cross the 2 millimeter mark when it is completely packaged. And as you go through the samples, you would get a feel for how much to put in there, so that after packaging you are going to get a capillary that looks somewhat similar to what we have here for B. You will need 3 such packed capillary tubes, and total 4 samples have to be done. That means each group would run beta-naphthol, everybody would run benzoic acid, you would run a mixture of beta-naphthol and benzoic acid, and you have a choice to either run acetanilide or urea. Okay, so the first 3, everybody has to do that. You have a choice for the acetanilide and urea. Total, that makes 4 samples per group, and you need 3 capillary tubes per sample. Since you would be working with a partner, it's a good idea to divide your work, and each of you should do at least 2 samples, so that you have a good idea of loading the sample as well as running it inside the melt temp and making an observation. You have to look through the eyepiece to be able to make your observations for an extended period of time. So now that we have our samples ready, let's see what we have to do with the melt temps. So the left-hand picture is the picture of what our melt temp would look like. We would have, like I said, the thermometer probe going into one of the slots. This is where you would look through, that's the eyepiece. And there are 3 slots for the sample. One of them is going to be your thermometer probe, and the other 2 are for your samples. The thermometer, the analog thermometer, will be placed in that aluminum cylindrical space, and this dial essentially can change, modulate the voltage going through. Of course, this one is just the power button. Since you already know the true values of these samples, other than the mixture, of course, you should start with the lowest melting point. This will save you a lot of time, because when you run your samples, you would first be carrying out the fast readings, and then you would carry out the slow readings. Now, how you want to do that? There's 2 ways of doing this, and I'll tell you that in a second. But in between one reading and another, you need to make sure that you cool down your melt temp by about 30 to 35 degrees Celsius. And the reason for that is, let's say you're doing a fast reading. Fast just means that you are providing the heat to that heating block at a increased rate. So the rate of the increase in that temperature is pretty high. This is going to cause uneven heating of the block, and it is going to give you a broad range. typically the higher part of the range is going to be slightly higher, because by the time you would be ready to read the dial, it would have gone up 2 or 3 readings. And so typically fast reading is not what you rely upon. In order to set the melt temp for a fast reading, you would want to use somewhere around 6, 7 or higher. That would be considered fast. Now, one might feel that if the fast reading has errors, why should you even run that in the first place? And the answer to that is that the fast reading will give us a tentative idea where the melting point is. And that is really useful when you have no information about the product and you have a completely unknown material. You get a feel for that fast reading. And then you can run your slow readings and get your confirmation that way. Now, in reality, you would always run the slow readings because that gives you even heating for the rest of the semester. But for this particular lab, you would be giving me one fast, and 2 slow readings. Okay. All right. So let's take a look at this first picture. This is kind of like a close-up of a thermometer probe and the 2 test samples. Hopefully you can see what's wrong with the 2 samples is that there's some, especially in this middle one, they did not take the time to powder, and which is why the result for the student also did not come out to be very nice. The second sample looks much better than the first one, but you can run 2 samples at any given point of time. This next sequence of the 4 pictures that I have, that is what I wanted to show you, and there is a video later on that you can watch where I'm trying to show you what the shrinking, that sweating of the solid, the sagging, and how it ultimately just melts away and gives you the clear melt in this final scenario. Notice that shrinking started to happen around 73 and the clear melt was formed around 75. So you would report, if this was your sample, you would report that as 73.0 to 75.0 degree Celsius, because this thermometer reads clearly as 70, 71, 72, 73, so each degree, and if it is in between, you would be able to read that as well. You're going to have to include that decimal to keep the least count. I should probably mention that every time you would be giving me the slow reading, you would be doing the slow reading at a dial of no more than 3. So the rate at which you should be heating should be approximately 2 degrees per minute is what a slow reading means. So it's if you find yourself heating at 5 degrees per minute or higher than that, so if it is more than equal to 5 degrees a minute, slow down. That will give you poor results. Let's take some time to talk about how you will record your data and how you should plan your experiment, what sequence you should run so that you can finish the experiment in a nice, effective manner. This observation table needs to be drawn ahead of time. So you're going to give me the compound, and this is where you're going to list what your compounds would be. You would write down the true value, and you would give me the citation, the reference that you're using that number from. You can use your book, the back of your book, the appendix has all the true values for all the compounds, and you can use that. In order to cite that, please use the ACS format, and it is the website address that you would be able to get that information from is on Blackboard under announcements. Blackboard announcements. So please check that for more details. You would give me the fast reading, so whatever the range was, let's say your first one was beta naphthol. I'm going to just give you a random number, not the correct number you're supposed to get. So suppose you got a fast reading, I don't know, 100 to 108 maybe, and then you did your slow reading, you got some number for that. That too is a range, slow too is a range, and then you would record an average for this. Now, average is done typically for the two slows, because like we said, those are more accurate pieces of data, so you're going to use those to determine your average. And if those two are numbers, let's say they look like 105 to 107 maybe, and 106 to 108. Maybe that's your data. That's what it looks like. Then the average is going to be, so you would have recorded 105.0 and 107.0, 106.0 and 108.0. So the average, you're going to take the two lows, you're going to find out the average for that and record that as 105.5 to 107.5. Please do not report an average of 105 to 107. Oh, that's 106. And then 106 to 108 is 107. And then taking an average of that. No, 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 no. We will not do that. Let me erase that. So let's make sure that everybody takes the average of the range and report it as a range. Okay, I want to see a range at the end of the day. You would then determine the percentage error for each of your samples, comparing those to the true values, and you can determine the percentage error from true value minus experimental value divided by true value times 100. So you would determine that, and then you would use that calculated error in figuring out your conclusion. So recall what I told you on day 1 of class. You would have written down the aim, materials required, equation, procedure in past tense, passive voice, and you would have drawn the observation table. So all that has to be done as a pre-lab. The calculation and conclusion is what you're going to work on as a post-lab, and you're going to end it as the post-lab in the post-lab questions, whatever is assigned, and you can find that in the student notes. So recall what I said on day 1 of class. Conclusion answers what you were seeking under aim. So the aim of this experiment was to determine the melting points of known and unknown compounds. That is the result. So you need to discuss your results here, and don't just retabulate your data, but talk about it. Talk about each compound. Talk about its percentage error and how well were you able to satisfy that goal. Maybe was that sample impure? So talk about the ranges that you're getting. Is that a big range? Is that a small range, or what? And compare the components of the mixture to the mixture itself and justify your result, your data. So those are some of the things that I would work on for the conclusion section, and then of course you would end it in the post lab questions and turn it in the next week. All of this, by the way, goes obviously on your carbon copy. You are expected to have that next week.